So we're continuing with the second half of this. So the other day we worked on problems that used the disk method and the washer method, but I had introduced both uh, that method and shell method to you. So let's just look over this one more time. So yeah, the two methods use different formulas that you should have in mind. Disk washer is these where you have a radius function that is squared and you have pi on the outside, versus shell method, which is what we're going to be using today. Um, Shell method, you have a 2 pi on the outside and you have a radius function times a height function, because both of these are what you would use to calculate the area of the cylinder. It's actually 2 pi times r times h. That's why you have the 2 pi outside there. That calculates the surface area of the cylinder. And then the idea of the integral is you're summing up a bunch of various cylinders that are all nested inside each other that would then construct that three-dimensional solid. One thing that I maybe didn't emphasize enough was actually the fact that you're not going to know right off the bat what the which method is appropriate for the problem. And so that's really the key question that you should be considering when you are looking at these problems or looking at them again. Because on the exam, for instance, it's not going to tell you which method applies to the situation, but usually it the structure of the problem will dictate which method is easier to use or which method like just overall should be used, because the other one is going to be far too much of a pain to implement. But overall, like structurally, these two things are these two methods in general are they both should apply. It's just a matter of like how complicated it would get to be to like cut up the region that you're considering to make one method work. So like, I guess I could talk about this a little bit now before we begin the next set of problems. But like, for example, if you take this region and you think about this revolution, you actually could construct this as a shell method type of problem. Like you could calculate this answer using shell method instead. But this red segment that we use to consider like what is the actual three-dimensional shape that is constructed, instead of it being vertical like this, it would have to be horizontal, so that when you rotate it with respect to the x-axis, then that actually traces out the cylinder, which would then make it a shell method problem. And then what you see is that that this upper area, or maybe it's not upper, maybe it's more lower. Yeah, this lower function actually behaves in two different ways. First, it's just equal to 0, but then afterwards it becomes a line. And the upper function would be this too. So what ends up happening is, to turn this problem into a shell method problem, you have to cut this region into a rectangle shape and a triangle shape, and then you end up needing to calculate two different integrals and add them together. So this is actually one of the more easier situations where you could actually calculate this in two different ways using the two different methods. Even better would be something like this, where actually all you need to do is rewrite the equations in order to recast the problem. So like to turn this guy into a shell method problem, again, like the red line ends up needing to be horizontal instead. And what that's going to do is it would make the integral be over the y-axis. And then all you do is you like solve these equations in terms of y instead, and then you integrate. So for this one, like it's just about resolving the equations, and then you'd just be able to calculate this using one integral. So this is also one of the easier situations. But now let's take a look at a situation which is kind of more problematic, which would be this one. This one, theoretically, you can reconstruct it so that it's a shell method problem, but you really don't want to, because in this case, right, we're revolving around the y-axis, and then so the red line, or the segment that you revolve, the segment that you consider, would have to go from one side of the parabola to the other side of the parabola. And the issue here is that this parabola is just given to you as one equation. You don't have right off the bat an expression that tells you for a given x value what that length would be. Um, so you'd have to think about it. And I think actually it's not too bad in this case. Yeah, it's just 2 times the square root of x, isn't it? Yeah. So here it's actually not too bad, but you can imagine that the situation would get much worse. And so that's why that's why I've been saying for a particular problem, you should kind of think like should it be one method or should it be the other, and try to consider like which method fits better for the problem, because um, in general you're not going to know right away just by being given a problem which method actually definitively applies. Like that is a deciding factor that you need to figure out as you're doing the problems. Um, but okay. Any questions before we uh, continue with the rest of the problem set? No? All right. Okay, so number 5, we've got this function y is equal to sine of x squared. These 3 lines, which should effectively bound the region we're thinking about. So let's go ahead and draw this thing and see what happens. So sine of x squared, for this, it kind of is a good idea to put this into a graphing calculator. You might be able to guess like what it roughly looks like, because you know what the sine of x function looks like. And then this x squared, like squaring that x is kind of just reshaping. It's like squishing and squashing. It's like just deforming how the x-axis appears. So you can kind of imagine it's like the signed function, except squashed together in some funny looking fashion. But graphing it is also just a good way to confirm your suspicions. And if you do graph it, you'll see something, well, it looks a little bit like that, but more, it turns out we only need to consider it up to the first, the peak, because it is, we're bounding our problem by x is equal to root pi, and x is equal to root pi. If you just plug that in, you get sine of pi, which is equal to 0. So you know it's like the first intersection that this thing actually does. And y equals 0, x equals 0, those are also just bounded. So this kind of shape is roughly what we're considering. And we want to revolve this around the y-axis, okay? And so, well, you can look at this shape and you can see that this would not make any sense, right? Trying to graph it like this wouldn't make sense. That this would be the if we were to try to construct them this way, we would maybe make the problem into a washer problem. But you can see that it's very challenging to do anything with that. So instead, let me undo. Computer's being a bit funny. I should be able to undo. Huh, weird. Okay. All right. So instead, we would consider this. Okay. And so now note that because we're revolving around the y-axis, this red line is going to trace out a cylinder. So this tells us that we're using shell method for this problem. And so shell method says 2 pi and then integral. We can put the bounds of the integral. We know that the red segment is going to go from 0 to the root of pi. You can just imagine scrolling it through the entire shape. Okay, and so then this is going to be with respect to x. That variable is changing with respect to x. And so now the last thing we need is we need a radius function and we need a height function for each of the cylinders that would comprise this integral. So the radius function in this case is the easiest thing possible. It's just x. What you do is you imagine like for a particular position for this red segment, what would be the radius from that to the axis of revolution. In this case, it's just going to be the length itself. It gets a bit more complicated if your axis is off one of the standard axes, which we will deal with in a later problem. But yeah, this is the radius function. And the height function is, well, just the height of that red segment, which, as you can see, is going to be the height of the function itself. So the function itself, that's this sine of x squared. And so we can just write it like so. Okay, so this integral is going to calculate for us the volume of evolution, and all we need to do now is to just calculate this guy. I want to pause here and make sure that you can see how you would integrate this, because it's important to know how to actually do this calculation. So hopefully you figured it out that time. The idea is that this is a fairly simple use substitution problem. You can let you really want to think of this inside of x squared to just be a single variable. So that tips you off that you want u to equal x squared. And then if you do that, du is going to be 2x dx. Okay, and notice you have this extra 2 lying about. So what we're going to do is we're just going to move that 2 inside. This is root pi. Well, if we're going to perform the u sub, well, let's not perform the u sub just yet. Let's just write it out in full first, so that we can make sure we all see this. Okay, so now this is completely set up for the u sub. It's going to replace the 2x dx by du, and it's going to replace the sine of x squared by u. So we have sine of u, we have an integral, and then of course we will want to convert the limits of our integral. So what it says is we end up squaring our x to convert it to u. So we just have to square these two limits, 0 squared and this root pi squared. So there we go. All of these were equal to each other. And then lastly, we integrate this guy. So we'll have a pi on the outside. The integral of sine is negative cosine. And then we evaluate from 0 to pi. Cosine of pi is -1, so this will become +1. And then minus, I think, -1. Yeah. So we get 2 pi is our answer. Okay. All right. Any questions on that? No? Okay. Right. The next, let's see, we've got y is equal to x, y is equal to x to the 8th, and we want to revolve around the y-axis. So y-axis is going like this, and y equals x is a straight line, y equals x squared is going to be something like this. And we know that the two things are going to intersect at 1. I think that's pretty clear. And so this is our region that we want to revolve. Now, for this problem, actually, you could use the washer method. You could rewrite the equations. So it turns out that that's not so bad. It's just you have to resolve these. But for this homework set, it probably makes sense to do this using shell method instead. The only difference is, well, I think actually shell method is harder to visually see than disk washer. But yeah, the added benefit is just you don't have to resolve the equations. You can just use the equations as given to you. So here, again, we have a color 2 pi integral. And so then this red segment is going to go from 0 to 1. You can see that from the picture. And well, the radius is just going to be the x value itself. Because again, well, maybe I should try to draw it. The radius is this distance, right? So for a given value, it's going to be the same, like x value. And then the height this time is actually going to be the subtraction of the two functions. So here it's going to be x minus x to the 8th, right? So this difference would calculate the length of that red segment. And then we integrate this with respect to x. And now we just go ahead and chug through the calculation. First, I'm going to simplify the inside. X squared minus x to the 9th dx. X cubed over 3 minus x to the 10 over 10. So that's just integrating. And then we evaluate. Let's see. If I plug in 0, it's 0. That's nice. If I plug in 1, I get a third minus a tenth. Um, 7/30. 2 times 7/30, but then I can cancel the 2, so 7/15 pi. Yeah. Right. All right, so next, y is 1, y is 5, x is 0, and then we have this x times y is equal to 1. So one thing you should know about this, like, is that this is a hyperbola, right? You could always just solve it and see that it is the one of the standard hyperbolas that you'd encounter. So it looks kind of like this. X equals 0, that's just bounding it. Y is equal to 1 is somewhere. Y is equal to 5 is somewhere else. And well, these are yeah, these are just bounding portions. So really this cuts away the shape that is here. And we want to rotate this around the x-axis this time. And so you can see that, well, we'll see if I can undo or not. But if you were to try creating the segment like this, you'd encounter a problem because the shape behaves differently at this intersection point. To the left of this intersection point, it's a rectangle. To the right, it's like some hyperboloid like triangular region. So you, theoretically speaking, you could do this using Washer method, but it would create a sum of two integrals that you'd have to compute separately. Whereas we can just compute this in one go if we consider our segment like in this way, and then we think of this as a shell method problem. Okay. Right. But in order to do this, then I actually don't want to think about this as a function of x. The way that it's written like this, y is equal to 1 over x, this is as a function of x. But here, this line is varying over the y-axis. So I actually want the integral to be in terms of y. Like we can already fill out part of the integral in this way. We would think of it as 2 pi integral from 1 to 5, and then we would say dy. We want to vary the y. So instead of this equation, we want to think of x is equal to 1 over y. And so now we're thinking of the same equation. It's just y is our input, x is our output. And well, here, y being our input, that's still totally fine. Our radius is just going to be the y value, which I've tried to draw in blue. It's just going to be whatever that length is. So that's radius, the radius function, and then multiply by the height function. Well, what would be the height function here? It's just going to be the length of the thing in red, which is governed by the equation of this hyperbola. So it's just the 1 over y. So we would multiply it by just 1 over y. Okay, well, that looks like a very simple integral because it simplifies to just integrating 1 dy from 1 to 5, which when you integrate, you end up with y on the inside, and you evaluate from 1 to 5. So you get 5 minus 1. So in total, you have 8 pi as the area, or volume, rather, because this is figuring out the volume of the solid revolution. Okay. Questions? No? Okay. All right. Well, then last problem. So now this is the more challenging of the, I guess, 3, 4 problems. So this time around, our axis of revolution is off-centered. We have it at x equals 3, and we're going to see what happens to this. So first of all, this function you actually should be able to picture without graphing it using a calculator. All you need to do is you factorize this. So 1 minus x is what you get, and that tells you this is a parabola. Sorry, this is a parabola with intersection points at 0 and at 1. And really those 2 points are all you need to do, all you need in order to trace out the parabola. So you have that, and then you have y equals 0. Okay, so that tells us that our region is this shaded portion. And then, well, now you want to revolve this around x is equal to 3. Okay, so that is here, and you want to revolve this about this line. Okay, so, well, the segment that you would pick should be this one, for which then tells us that we're using Shell method. And so we have 2 pi, we have an integral from 0 to 1 with respect to x. And now we think about the radius function and the height function. So the height function is actually the easy one in this case. It's just the function that's given to us. So I'll just write that down. Okay, that's the easy part. The radius function is where we have to think about this a little bit. Okay, because you can see that because this axis is off center, it's actually adding something to the radius. So I think the way I would recommend thinking about this is kind of by considering examples in a way, like consider 2 different places where consider the 2 different extremes of where this red line could be. It can be at 0 and it can be at 1. And then we can kind of construct from there what the radius function should be. So like say that the red line is at the 0 place. So that's x equals 0. And then we think about what is the radius? Well, we go from 0 to 3. So the radius should actually take the value 3. And the other extreme is when the red line is at 1. So in that case, x would be equal to 1. And you can see that the radius there is the difference of these two. So 3 minus 1, radius is 2 in this case. Okay, so what's happening is that when x goes from 0 to 1, you want the function to go from 3 to 2. And you can kind of anticipate also, like as this is moving, the radius function is also varying in a steady fashion, meaning like it should be a line, it should be linear. The radius function should be linear. And so I don't know if this makes sense intuitively or not to you guys, but this, at least to me, tells me that the radius function is 3 minus x. But now that I've written 3 minus x, maybe it's even more clear to you because you can think about this algebraically. So this is one other way we can think about this. For some given distance x that you're, for this particular cylinder or cylindrical piece that you're considering, you would then have to calculate the radius to the distance 3. And what you can see is that that radius, r, is going to be, well, 3 minus x. So it's just comparing 2 different lengths. To me, I find this to be more intuitive, but this is much less problematic for like poking holes into. Like this is very airtight, but it's not the immediately obvious thing for me. Okay, but hopefully that convinces you then that the radius function is 3 minus x. Okay, so this integral that we've set up will calculate for us the volume of the solid of revolution. And then we just go ahead and compute this guy. So what's bothersome here is we have to expand this thing out completely. There's not really an integral trick to do that. Like, well, we can't really do a u sub. It doesn't really fit in that mode. So instead we expand this out. And if we do that and simplify, we'll get this polynomial. And that is pretty straightforward to integrate. So 3x squared over 2 minus 4/3 x cubed plus 1/4 x to the 4th. And then we would evaluate this from 0 to 1. Plugging in 0 will just give me 0 for everything. So I don't really need to consider that. but plugging in 1 is going to give me a bunch of fractions, which I'll just tell you what that ends up amounting to. That'll give you 5/6 pi at the end. Okay. So, are there any questions on anything? Oh, okay. If not, I'm going to stop the recording.